Hi there, my name is Mr. Chick and I'm here to tell you about forces and motion. This video has been designed to help students understand about both forces and motion and how they are related. I have a sequence of videos here that covers forces, motion, momentum, work, and energy. Okay, so we'll look at momentum now. Momentum is a measure of how hard something is to stop. The momentum of an object is its mass multiplied by its velocity. If something is heavier and faster, it has more momentum. The formula for calculating momentum is as follows. Momentum equals velocity multiplied by mass. Momentum does not have any special units, it is simply measured in kilograms meters per second, as mass is in kilograms and velocity is meters per second. In the example below, both balls have the same momentum. They both have 14 kilogram meters per second. This is despite their masses being different. As you can see, the bowling ball has a much heavier mass, a much larger mass than the tennis ball, but the tennis ball has a much greater velocity. Therefore, they can both have the same momentum. Momentum is related to inertia. Inertia is Newton's first law of motion. An object's inertia means it wishes to stay at rest or continue moving with a constant velocity. Momentum is a measure of an object's inertia. Just like energy, momentum is conserved. You can't destroy or create momentum. If a moving car hits a stationary cart, they will both move. Obviously, their mass will not change, but their velocity does. This means their momentum changes. The stationary cart gains momentum, whilst the moving cart loses momentum. We can see the same event happening with astronauts in space. Because there are no resistant forces in space, it is a good example to show the conservation of momentum. You can see that the right astronaut is stationary, and the left astronaut comes in with quite some speed. As they collide, they both move away together at half the speed that the astronaut was moving at. But now, of course, their mass is doubled. The mass of the two of them is doubled, so the momentum is still the same. If two carts are stationary together, they have no momentum. This is because they have no velocity. If one pushes off against the other, then they both gain momentum as they both move away. They both have velocity, so they both have momentum. Remember that velocity can be negative because it is speed with direction. This means one cart gains positive momentum and the other gains negative momentum. The positive and negative momentum add up to the sum of 0. Cars are packed with safety features designed to work in the event of a crash. Airbags, seat belts, and crumple zones all work on the same principle. They're designed to slow down the change in momentum. The change in momentum can be calculated using the following formula. Change in momentum equals force multiplied by impact time. In a crash, you will change speed from whatever you were traveling down to 0. This is because the car comes to rest. It also means your momentum changes to 0. This means your change in momentum is equal to the momentum you had before the crash. So that makes things easier when it comes to calculations. The change in momentum can be calculated using the following formula. Change in momentum equals force times impact time. So, in a crash, you can't change your momentum. You can't change the change in momentum. However, you can increase the length of time it takes you to stop. Doing this reduces the force exerted in the crash, or in the impact. Airbags, seatbelts, and crumple zones all increase the time it takes to stop. Therefore, they all reduce the force exerted in the crash. Energy and work, finally. So, Work done is the energy used to move an object through a distance. It is the amount of force applied multiplied by the distance moved. This is calculated using the following formula. Work equals force times distance. If a force is applied but the object does not move, then no work is done on the object. Work done is energy transferred. It's the energy transferred, so it is measured in joules. However, it is also right to use the units Newton meters, as this is a force multiplied by distance. Work equals force times distance. If an object is lifted up, then the force is the weight of the object. If you were to go up some stairs, the work done is your weight multiplied by the distance moved. Remember that the weight of an object is its mass multiplied by 10. Kinetic energy. Einstein's famous equation is E equals mc squared. We use a similar equation to work out the kinetic energy of an object. Kinetic energy is movement energy or energy of a moving object. We can calculate this using the formula half times mass times velocity squared. This links to Einstein's equation because E is energy, m is mass, and v squared, or c squared, c is the speed of light. So this is how it's related to that. So kinetic energy equals half of the mass multiplied by the velocity squared. It says that if you double the mass of an object, the kinetic energy doubles. If you double the velocity of an object, the kinetic energy quadruples. This is because the velocity is squared, which means you multiply it by itself. Gravitational potential energy. The gravitational potential energy is the potential energy an object has to move. This is because gravity has the potential to pull the object down. This can be calculated with the following formula. Gravitational potential energy equals the mass times gravity times height. It is the height the object is off the ground multiplied by the mass of the object and the acceleration due to gravity. In other words, it is the height multiplied by the object's weight. Let's say an object is lifted vertically up from the ground. The work done on the object is equal to the gravitational potential energy. This is because the formulas are exactly the same. So, gravitational potential energy equals mass times gravity times height, and work equals force times distance. The mass multiplied by gravity is weight, and weight is a force. The height is the same as the distance moved. These are only the same if the object is lifted vertically up. If it is not moved vertically up, it is moved diagonally, and obviously the distance moved is bigger than the height lifted, so the work done is going to be different to the gravitational potential energy. It's going to be more. Kinetic energy and work. Let's say an object is moved horizontally along the ground. The work done on the object is equal to the kinetic energy of the car. This is only true if there is no resistant forces such as friction. These are only the same if the object is moving horizontally. Again, if it is moving diagonally up, then some of the energy is stored as potential energy rather than being kinetic energy. Have a look at this one here. Kinetic and gravitational potential energy come hand in hand. Energy is conserved, which means it can't be created or destroyed. It is transferred between kinetic and gravitational potential energy. You can see in this diagram here. When we look at this pendulum, as an example, there is no kinetic energy as it is all stored at potential energy at the top. At the bottom, all of the potential energy has been transferred into kinetic energy. Halfway up, or indeed halfway down of its swing, half of that energy is going to be potential, and the other half is going to be kinetic. The pendulum mentioned will not swing forever, however. Likewise, a ball that is bounced will not bounce forever. This is because some of the energy is transferred to the environment. This means that not all of the energy is transferred between kinetic and potential energy. In almost all circumstances, some energy will be lost as heat. This is usually a result of friction. Energy is also lost as sound, of course. Both sound and heat energy are dissipated or transferred to the surroundings. I've been Mr. Chick. I hope this video has been helpful to you. Thank you for watching.